So when we calculate the mean, it gives us an idea of expected value. So what we expect for our data set. But with just an expected value, we sometimes want a little bit more information. And with that, we want to get an idea of the spread of the data. So while we expect to land at one point, it's like, but how much do we expect that to differ? And that's where standard deviation comes in. It describes the spread of the data. So that if I made a statement and said something like the average age of my students is 25 years old, with that you can have an idea that a student walks into the classroom, I expect them to be 25 years old. But I could add more to that statement of say, I expect them to be 25 years old, and on average that differs by about 1 year. Then you get this kind of window of 1 year around that age of 25. So then we get this idea of, okay, we really expect them to be 24 to 26 years old. So we get this window. And then you could see how the spread changes where if, let's see, I said 25, and then I used that example just now of spread of 1 year. I need to write this down so I don't mess it up. But then let's say I calculated the mean is 25 years old, and on average that differed by about 5 years. Then we'd end up with this larger spread. We'd expect students to be anywhere from 20 to 30 years old. So then there's more variability coming through. And that's what standard deviation is going to do, is that while we have our mean, it's on average, how do the values differ from the mean? And with that, we can get this window around where we expect, kind of go below and above with this distance to get more of almost a range as the idea of where we expect to land for our data. So with this, what we want to think about is this difference from the mean in terms of each of our data values. How does it differ from the mean? And what we want to end up taking is this average distance away from the mean. That is the idea of standard deviation. So there are some pieces here. We have the word average coming through, so that's going to be part of our calculation, and then distance away from the mean. So with our data values, we want to think about how far away from the mean are they. So to begin to just think about distance away from the mean, let's look at this example. Let's say we have 4 students sitting at a table and we have their ages 22, 19, 19, and 36. So to get distance away from the mean, the first thing we need to calculate is the mean. So calculating the mean, add them up and divide by how many there are, which there are 4 students there. So that'll be an average of 24, and I'm going to go ahead and throw in the units here because we'll talk about units a little bit. Or I'm going to simplify it of just years. So for age, 24 years. So then what I want to get at is this distance away from the mean, and that's where this term deviation comes in. What we're going to do is look at this difference between each data value and the mean. So the differences, I could take my first data value of 22 and subtract the mean of 24, and then have my next data value, minus 24, the next, minus 24. So then we could get this idea of how far away they are from the mean. So if I calculate these, I'll have a -2, -5, -5, and 12. Now this gets an idea of not necessarily distance, but a measurement of how far away we are from the mean, but we have these negatives and positives coming through. So what we need to do is make an adjustment so that it does fit this idea of distance. So when we get here, we get a little stuck because we can't use negative values. Or rather, we'd rather everything come up as positive. So rather than -2 showing up, we'd want a positive value to represent that distance. Now, there are a few different ways of making negative numbers positive, and absolute values is one of those cases if you've learned about absolute values before. However, with statistics and specifically with standard deviation, it ends up adding error in a way in terms of long-term calculations. So we can't use absolute value. So instead what we're going to do is square the values. So what we're going to do is, instead of just using the deviations, we're going to look at the squared deviations. So we'll take those same values of the data value minus the mean, but we're actually going to square it. So instead we're going to look at 22 minus 24 to get the idea of distance, but to make sure that it's positive, we're going to square it. Same thing with 19. And it's because we square each of these, it's under the same operation. So we're getting these positive numbers and they're scaled in a way that matches up with each other. So with that, we're getting 4, 25, 25, 144. So with this, it's essentially these squared distances that we're getting. So we're going to make up for this later, but it's just a step we have to take in order to think about distance away from the mean. So what we end up with here is squared distances. So before we take care of these squares, our next piece is to think about average. We want to average the distances. In this case, we're going to end up averaging the squared distances. So to do this, what we would do is add up these squared deviations. So what I'm going to do is add up the squared deviations and then divide by, and then we usually divide by sample size, and I'm going to make an extra note there in one moment. But just to write this out in long form, just so you can see everything at work here. So we're going to add up those squared deviations. And then divide by how many values there are, which would be sample size, which in this case you want to think about at the beginning with this data set, there were 4 values. So we have this sample size of 4. Now, there's another little twist here because, and it's hard to explain without going too far into statistics, but if you just trust me with it, if we divide by 4, it actually introduces some error. So to make up for that, we need to subtract 1 away. So in the denominator, we're going to divide by sample size minus 1. This idea of sample size minus 1 is also called degrees of freedom, a very fancy way of saying sample size minus 1. But what we're dealing with here is this is how we have to average these squared distances. So we have our squared deviations added up in the numerator, and then the denominator sample size minus 1. So if I calculate that, this value is going to come out to be 66. Now we have average. We don't quite have distance away, we have squared distance away from the mean. So if we follow our units, if we started with our units of years, here when we took the deviations, we did have these differences of years. It's just we ended up with those negative values. But then when we squared, we ended up with these values that are years squared. So this is where our units are kind of weird. Like 4 years squared is a hard concept to understand. And then here when we averaged values that were in years squared. So the 66 technically has units of years squared. So it's still kind of strange. This value of 66, this is called the variance of the data. Some symbols you might see for variance would be s squared or sigma squared. Both of those symbols represent variance. So it'd be this act of adding up the squared deviations and then dividing by sample size minus 1. But what we want to get to is standard deviation. And to do that, we basically want to undo the square on our units. So what we're going to do is take a big square root. So what we're going to have is the square root, and I'm just going to write it out long. It comes down to the square root of 66, but it's that we're taking the square root of these squared deviations added up in the numerator. And then in the denominator dividing by sample size minus 1 with the idea of taking the average. So this will be the square root of 66, which will be 8.1240. And then by taking the square root, our units are back to where we want them in terms of years. This calculation right here overall is our standard deviation. So standard deviation will always have this big square root, and then in the numerator, adding up the square deviations, denominator, sample size minus 1. Now how this can translate into a sentence, and I gave a structure here that you could follow to help making sentences relating the mean and standard deviation, but it's that idea of what I was talking about at the beginning here of like the average ages of students, and then getting this idea of a window of how we expect that value to change. That's mean and standard deviation working together. So I could say is the mean age at the table is 24 years old. And on average, it will differ by, and then our standard deviation. Let's go ahead and round, I'm going to round that to a whole number. Let's say about 8 years. So the mean and standard deviation should always have the same units, and that's how they can relate really nicely in a sentence. And then it's the mean is the idea of center, it's where we expect to land, and the standard deviation tells us on average how that value will differ. Now, to show you how you would calculate this all together in a calculator, all right, so if we're in Desmos, we're going to start our square root, and then what you can do is separate your numerator and denominator, and then it's just a matter of typing everything in, and then you can just have it line up with how you wrote it on your paper. So I'll just show you typed out plus, and then 19 minus 24. And finish writing that numerator, and then we can go into the denominator. And you know, often with the denominator, you'll want to write it out on your paper, like typing it in 4 minus 1, that'll be 3, or you could type it in as 4 minus 1, and then you could see your standard deviation. Now I want to show you a function here. It's good to know how to do standard deviation by hand, and it's not too bad for these small data sets that we have here. However, when you're doing my open math homework and you're getting larger data sets out, it can be pretty tedious to do standard deviation by hand. And in the next example, I'll show you a way of kind of organizing your work that can help out. But what's nice about the Desmos Calculator is if you see these functions here, so there's main, ABC, and then function. If we go over to function, what you'll see is underneath the trigonometry, you'll see mean and standard deviation. So what you could do here, if you're doing lots of problems and just need to get the calculation, and this is totally fine by me, I like to show the formula and show you how it works because I think it does help in terms of interpretation and seeing that it's this average distance away from the mean. But if you need just a quick standard deviation, you can use the Desmos Scientific Calculator, and what you'll do is click standard deviation and it'll open up these brackets, and then all you have to do is type in the data. So like with our data set 22, 19, 19, 36, and you can see that same value there. So if you need a quick standard deviation, that's a great way to do it. Let's go back and look at another example. Oh, sorry, here's a breakdown of how you'll find standard deviation. And with this, we get kind of how we want to summarize symmetric data like we were talking about in the previous video. We'll want to use the mean and the standard deviation to describe center and spread. And calculating standard deviation, you'll have this big square root, Then in the numerator, add up those squared deviations, denominator, degrees of freedom, which is sample size minus 1. All right, so let me show you how to kind of break it down. Then it might be easier, or if you're good with plugging this in all at once, that works great too. But I'll kind of show you ways to maybe make it a little simpler here. So first thing we're going to need is the mean. So you'll always have to start there. So I'm going to add up the values and then divide by how many there are. And that should give us a mean of 11.2. And then what can help in terms of organization is just listing out the squared deviations as a table. I kind of did that in the previous example. What I'm going to do, and let's see, we have 5 data values. So I'm going to have these 5 values squared. And I'm going to take each data value, 3, 8, 12, 15, 18, and then I'm going to subtract, and then the mean for each of them. So with that, you can kind of see the structure for your square deviations. And what I want to do is add those up. If I do that, that'll give me the numerator for my calculation. So if I'm getting standard deviation out, and sorry, I meant to mention this, and I'll just write it before I forget it. Some notation you might see for standard deviation is a common symbol is S or sigma. So we actually saw that with variance. Variance was S squared or sigma squared, and the idea is we did just take the square root. So the symbol for standard deviation is just those same values without the square. So if we want standard deviation, in fact, I will just write S here for standard deviation. We want the square root, and in the numerator, we want the sum of these squared deviations. So with this broken down, it can be a little easier to type into the calculator. So taking 3 minus 11.2 squared, and so on and so forth. Sorry, it's hard to type. If you want to fast forward along, I'm kind of a slow typer. All right. In fact, I know what it's going to come out to be, but just to get there, 15 minus 11.2 squared, and then our last one, all right, 138.8. So that's going to make our numerator. If this comes out to kind of a messy number, just make sure to round to at least 4 decimal places for plugging into standard deviation. This rounded pretty nicely to 138.8. So then going to find standard deviation, for my numerator, it's that sum of the squared deviations. So then I can just plug in a single number for that numerator instead of like how I did back here with kind of a long list. And then for the denominator, that's going to be a 5 minus 1, or when we get to the calculator, we could just type in 4. So with that, I'll go square root 138.8 divided by 4, and it's just a little easier to type into the calculator. So 5.8907 is our standard deviation. So let's say we put some context to this and said this was the number of people visiting a certain cafe on 5 randomly selected days. So the idea being that one day they had 3 people stop by, one day they had 8, another day 12, another day 15, another day 18. So just to get in terms of a sentence, so you could say is we expect 11 people to visit. So let's say the cafe can expect about 11 people to visit in a day. So let's say people each day, and on average, this will differ by about 6 people. So the idea being for this data set, we expect 11 people, but we could expect like 6 less than that or 6 above that. And what you can kind of visualize, so 11 is landing about here in our data set. And then we've made this range of 6 below, so like 5, and then 6 above, 17. So it does cover most of the data. It does leave out these kind of tails, and especially with a small data set, it's going to be a little strange. But it does set up this range of expecting 5 to 17 people, does cover most of the cases when we look at that. So that's mean and standard deviation working together. With the standard deviation, when I get to the end there, I do recommend you can use this function to check your answer too. So if we get to the end there, and just to make sure we did it all right, there's the solution that we got. So no problem. So that can be a good tool when you do the final exam as well. If I ask you to show any work, be sure you show work, but to check your answer, you can always run over to Desmos and use that standard deviation function. There are also standard deviation functions in Microsoft Excel and GeoGebra, so you can use those different tools as well.